This is the next video in the chapter on chemical bonding and molecular geometry. We just talked about what a covalent bond looks like and how it involves the sharing of electrons between two atoms, but we hinted that not all sharing is equal. And that is true because of another periodic trend that's called electronegativity. So the punchline for this section, not all sharing is equal. And so we need a way to describe whether a particular atom is willing to share or is not very good at sharing. And so we can use the new periodic trend called electronegativity. And you can see over on our little table over here that it is the largest and most positive towards the top right corner of the table, with the exclusion of the noble gases. So electronegativity is defined as a measure of the tendency of an atom to attract electrons in a bond. And I know what you're thinking. You're thinking, gosh, this definition sounds an awful lot like a definition that we talked about in a previous chapter. It sounds an awful lot like electron affinity. So let's just be super clear and spell out the ways that those definitions are slightly different, so everybody's on the same page. We're going to do red emphasis for electronegativity. We're going to do blue emphasis, electron affinity. So electron affinity first, because that's the one we learned about first. So electron affinity is a measured value, something that you have to perform an experiment to find out about. And the electron affinity specifically is a measure of the amount of energy that's absorbed or released when an anion is formed. Remember, this is the weird one where it could be positive or negative, but it's about an energy transaction. Okay, and so now let's compare that to electronegativity. Electronegativity is not measured, it's calculated. This is a theoretical system invented by Linus Pauling, which is on a 0 to 4 scale, so it's always positive. And on a scale of 0 to 4, each element receives a number that indicates how tightly an atom attracts an electron in a bond. So let's be really clear about the differences. Electron affinity, measured value. Electronegativity, calculated. Gosh, they even sound a little bit the same. Electron affinity is about forming an anion. Just one atom, negative charge, chilling by itself. Definitely not associated with anything else. Don't need no man. Electronegativity is about an atom attracting an electron in a bond. So this is how an atom behaves in groups. And the final point we can use to compare them, electron affinity is a description of how well an atom takes. And remember, we use the word take to describe ionic bonding. Definitely super not sharing. And electronegativity is a measure of how poorly an atom shares. And sharing was a property of covalent bonding. So very electronegative atoms do not share well, and atoms with a high electron affinity are really good at taking an electron from something. So this is really the major defining feature of how a covalent bond is different from an ionic bond is that in a covalent bond, there is this sharing happening, and the amount of sharing is related to the electronegativity value of a particular atom. So we're going to make a table to relate that information together. So it's going to have electronegativity difference of the two atoms in the bond as the main feature. And that electronegativity difference is going to indicate the bonding type. And then we'll give an example molecule that shows that type of bonding. It's going to be roughly this big. Okay, so we are going to go from small to large electronegativity difference. So if we have a small electronegativity difference, then this means that the atoms are really similar to each other and they are going to share very well. So their ability to share is going to be similar. So this is called a pure covalent bond. And an example of that, if you could try and think of elements with similar electronegativity, the most obvious choice is two atoms that are the same. If the atoms are the same, they have the exact same electronegativity, so the difference between the two electronegativities is almost zero. That's called a pure covalent bond. This definition also extends to atoms that have very similar electronegativities. They don't necessarily have to be the same atom. So what if we had like a medium electronegativity difference? So the electronegativities are not the same. They're not super similar, but they're still not different enough that we can start giving and taking. They still both kind of want to share. So this is a subset of covalent bonding, and we're going to give that a special name. We're going to call it polar covalent bonding. And we'll talk more about that in a second. And an example of a polar covalent bond might look like this. So the chlorine is very electronegative. It's very close to that top right corner over here. And the hydrogen is somewhat electronegative. It's sort of in the middle in this new position we've given it. And so they have somewhat of a difference, and chlorine is going to be hogging most of the electron density. The last line in the table is if you have two atoms and they have a large electronegativity difference. And if they have a large difference in electronegativity, that means that one atom is going to be really great at sharing and one atom is going to be really terrible at sharing. And we both know that when a relationship is not balanced, that sharing does not actually happen and one takes advantage of the other. And so this results in ionic bonding. So when one atom is very good at sharing and one atom is very bad at sharing, they do not actually share. The one who's good at sharing gives the electron, and the one that's bad at sharing takes the electron. And you end up with an ionic bond. It looks something like this. We don't actually draw the line between them. We just draw them close together with their respective charges, and we understand that that's an electrostatic ionic bond. And remember, not a molecule, it's a ratio or a formula unit. Okay, so I just threw this new term on you, so let's take a second and look into that new term, this special polar covalent bond, and how that's different from a pure covalent bond. So we said that a polar covalent bond represents a situation where the electronegativity difference is medium. You have something on the right side of the table and something that's more in the middle of the table bonding together, like HCl. And what that looks like in terms of where the electrons live is the electrons want to live closer to the more electronegative atom, which is chlorine. So we would draw sort of an outline of where the electron might live, as a lot of the time the electrons would live near the chlorine, and a little of the time they would live next to the hydrogen. So the electrons still live next to hydrogen sometimes, so we haven't totally formed an ionic bond, but this is definitely not equal sharing. The electrons spend more time over here than they do over here. And we can indicate that in the picture by using a little lowercase Greek letter delta. And we put a lowercase Greek letter delta plus next to the less electronegative side, and the lowercase delta minus next to the more electronegative side, because having the negatively charged electrons by this side for longer makes that a slightly negative charge. It's not a full positive charge, so the electron doesn't completely belong to this side, so we can't just write negative, so we write this symbol to indicate it's a partial negative. So let's write that. Chlorine is the more electronegative of the two. So more of the electron density of the bonds is on this side. So this is sort of how we understand where the electron might live. And another way we indicate which side is the more electronegative side of this bond is we draw what's called a dipole arrow. Oh, and we'll write delta so you remember what letter that is. So this is called a dipole arrow, and the dipole arrow points toward the more electronegative atom in the bond. Running out of space, we can fit it. There we go. So the way you can remember that it points towards the more electronegative is if you put a little slash on the back end of it, so that that end looks like a plus. So it points from the plus, slightly positively charged end, to the slightly negatively charged end in a polar covalent bond. And then just for contrast, if we had a pure covalent bond, our example on the last one was 2 chlorines, we would outline that electron density as being more even, as spending a more even amount of time around each of the 2 atoms. So defining an electronegativity value for each element helps us to predict when we see a bond form, whether that might be more of a sharing situation, like a pure covalent or a polar covalent bond, or it might be more of a give and take situation, like an ionic bond. And that helps us predict the properties of the compound, the number of valence electrons that each atom has complete control over or shared, and where the electron density might be. Now that we've finished talking about ionic bonds and covalent bonds, we need to check it off in our atoms first approach diagram. So our first learning objective under molecules was to learn about bonding types. And the next one will be Lewis structures and nomenclature.